Hello everyone, welcome to my YouTube channel. So today I am going to discuss CSIR NET December 2023 real analysis solution. So the first question says that let f from R to R be a differentiable function such that f and its derivative f prime have no common zero. Then which of the following statement is true? So observe that this first option and the fourth one, this is this is not, it is clear that this is not true, right? Why? Because simply if you take a function like that, so just draw a graph. So let's take a function like this, then say f of 0 equal to f of 1 equal to 0, and then f prime sum, say this point is some c, f prime c is 0. Then clearly f and f prime both have different zeros, they have no common zeros in 0 1, and also f of half is not equal to 0. So clearly these two statements are false, right? Now the interesting fact is that we need to show the actual answer is that f has at most finitely many zeros. Okay, so how do we prove that f has at most finitely many zeros? Because you can take a example and conclude that, but how do I prove that, right? So the solution, so let f has infinitely many zeros. Okay, f has infinitely many zeros, and consider xn be a sequence of zeros. Okay, since f has infinitely many zeros, you can choose xn to be a sequence of zeros such that xn not equal to xn different, right? So because it has infinitely many zeros, and since xn is bounded, why it is? Because it is inside closed interval 0 1, right? Xn is bounded, so by Bolzano-Weierstrass theorem it has a convergent subsequence, so xnk be a convergent subsequence converging to x. Now by continuity of f, since xnk converges to x, f of xnk converges to fx. Now xnk all at 0, right? That means f of xnk equal to 0 for all nk. So this will imply fx equal to 0. That means in particular x is also a 0 of f. Now f is differentiable, right? F is differentiable. This will imply f prime x exists, right? For this x, f prime x exists. Now by sequential criteria, for any sequence yn converges to x, f prime x is same as limit n goes to infinity f of yn minus fx by yn minus x. Fine. So in particular I can choose this yn to be our xnk. Then f prime x equal to limit n goes to infinity f of xnk minus fx by xnk minus x. Now f of xnk is 0, fx is also 0, so f prime x is 0. This will imply x is common 0 of f and f prime, right? X is common 0 of f and f prime. Okay, so that's why f can have at most finitely many zeros, because if f has infinitely many zeros, we'll take distinct term, distinct zeros, and that has a subsequence converging to some particular point, and at that point must be the common zero of f and f prime both. That's why f has at most finitely many zeros. It's a very nice problem. Okay, move to the next one. The next problem is also very nice. It is given that f is a real valued function defined in this way and f prime be its derivative. Then we are considering set of all c such that f prime x is less equal to c times fx for all x belongs to R. right? So consider gx equal to fx times e power minus cx. Then g prime x equal to f prime x times e power minus cx minus c times fx e power minus cx. So this will imply e power minus cx times f prime x minus cfx, right? Now we assume that such a c exists, right? Such a c exists. Then f prime x minus cfx, this is less equal to 0, and e power minus cx is greater equal to 0. That will imply g prime x is less equal to 0 for all x belongs to R. And if g prime x is less equal to 0 for all x belongs to R, that will imply that g is decreasing. G is decreasing. That means for any x belongs to R positive, in particular x greater than 0, gx is less equal to g0. Now g0 equal to f0 times e power minus c times 0, which is same as f0, and by given condition on f0 is 0. So hence gx is less equal to 0 for all x, sorry, yes, gx is less equal to 0 for all x greater equal to 0, right? And again from given condition, if I see gx equal to fx times e power minus cx. Now this e power minus cx is always greater equal to 0. That means gx less equal to 0 implies fx less equal to 0 for all x greater equal to 0, right? So for all x greater equal to 0. Again fx equal to 1 minus x square times sin x square for x belongs to 0, 1. And clearly for this fx is strictly greater than 0, right? Because x belongs to 0, 1. X belongs to 0, 1, so fx equal to 1 minus x whole square times sin x square for all x belongs to 0, 1, so fx greater than 0. Hence this condition is wrong. That is a contradiction. So this will imply that no such c exists. Hence no such c exists, right? No such c exists. That means S is empty. Okay. So this is a nice problem, a very conceptual problem. Okay, move to the next one. So we need to know what is definition of lim sup. Then it is easy to do. So if an be any bounded sequence, okay, before going to state that theorem, first let me write what is lim sup of an. So lim sup of an, okay, so first define a sequence Bn as, say, define a sequence Bn equal to supremum of an comma an plus 1 comma an plus 2 and so on. This is a sequence. Now take the limit of Bn, that is called lim sup of an. So limit of Bn is called lim sup of an. So if an is bounded, you can check, or it is a, you can assume it as a theorem. You can see the proof in any book that if an is bounded, then lim sup of an is same as supremum of limit points of an. So as an example, so take an example, say an equal to minus 1 to the power n. Okay, that means an is given by minus 1, 1, minus 1, 1, and right. Then limit points of an equal to 1 and minus 1. Hence lim sup of an means it must be 1. Now this is homework. You can do that. You already know the definition of lim sup. Now check the definition and see that lim sup of n and lim sup of a to n and so on. Okay, move to the next one. So let fx be a cubic polynomial with real coefficients, and suppose that f has exactly one real root and that root is simple. Then which one of the following statement holds for all antiderivative capital F of fx? So antiderivative of small f means, so f is called antiderivative of small f if capital F prime x equal to small fx. Okay, say capital F is called antiderivative of small f if capital F prime x is small fx. Now we'll use Rolle's theorem. Okay, we'll use Rolle's theorem. So see, so it is given that capital F prime has exactly one real root, exactly one real root. So it is given that capital F prime has exactly one real root, and the option is given the how many root can capital F have, right? So if f prime has exactly one real root, then f can have at most two real root. Why is it? Because if f has three real roots, say, then by Rolle's theorem, say a, b, c are the roots of f. Okay, fa equal to fb equal to fc equal to 0. Then by Rolle's theorem, there exists some d belongs to a comma b and say e belongs to b comma c, such that f dash d equal to f dash e equal to 0, right? So if it is a, b, c, then there is some d here, there is some e here, right? Such that f prime, these are the roots of f prime. But it is given that f prime has exactly one root. Hence f can have at most two real root. Okay, that's why this f has at most two real roots. This is correct. And you can easily construct the other options counter example. That is your homework. Fine. Move to the next one. Consider the following infinite series. A is sine n pi by 2 by root n. So a equal to sine n pi by 2 by root n. So how the terms looks like? See, if n is even, then an equal to 0, because if n is even, then sine pi, sine 2 pi, sine 3 pi all are 0. Hence an is 0. So the series summation n greater or equal to 1 is actually looks like 1 minus 1 by root 3 plus 1 by root 5 minus 1 by root 7 plus 1 by root 9 minus 1 by root 11 and so on, right? Then by Leibniz test, this is alternating series, and 1 by root n type series is monotone as well as converges to 0. Hence this alternating series is convergent by Leibniz test, right? This is convergent. And the second one, say bn equal to log 1 plus 1 by n square. So limit n tends to infinity, bn by 1 by n square equal to 1 by definition. Hence by limit comparison test, summation 1 by n square is convergent implies summation log 1 plus 1 by n square is also convergent. Hence both a and b are convergent. Move to the next one. So let X be any non-empty finite set, and we are considering a collection Y which is collection of all f inverse 0, where f is a real valued function on X. Okay, so then which of the following statement is true, right? So see, observe. So take any subset of A. Take any subset A of X. Now define a function, say f sub A, such that f sub A of X is 0 if X belongs to A, 1 if X belongs to A complement. Fine. Now clearly f is a real valued function because it takes real number as its value, right? So f is a real valued function and f inverse 0 is precisely A. F inverse 0 is precisely A. And that means you can take any subset of X and do the same process, right? To proceed the same way, you will get a real valued function such that f inverse. So that will imply that this collection Y is power set of X, because any subset of X is in this Y. So that means this collection is power set of X. So cardinality of Y is same as 2 power cardinality of X, because cardinality of power set of X is 2 power cardinality of X. Now X is finite, that means 2 power cardinality of X is also finite number. So Y is infinite set, that is false. Y has 2 power X, 2 power cardinality of X element, that is correct. Now we are going to use an important theorem from set theory, basic theorem, and the most important theorem from set theory, that is called Cantor's theorem. So Cantor's theorem says that there doesn't exist any surjective map from X, where X is non-empty set to its power set. Okay, there doesn't exist. That means there doesn't exist a surjective function from X to Y, because Y is actually power set of X, right? So this there doesn't exist, that means this option is false. And there is a bijective function, that is also false, because there is no surjective map itself, so there is no point of having bijection. So only second one is correct. Okay, move to the next one. Consider the following subset. This is a very simple problem. So x square minus 9x plus 18 is basically same as x minus 6 times x minus 3. So this is less equal to 0. This will imply 3 less equal to x less equal to 6. Similarly, x square minus 7x plus 12, that is less equal to 0, implies x minus 3 times x minus 4 less equal to 0. That means 3 less equal to x less equal to 4. Okay, so hence infimum of u is 3. Fine, move to the next one. So An be a collection of non-empty subsets of Z such that An intersection Am is empty and Z is union of An. So since An is subset of Z, this will imply An is countable. An is countable, right? For any n. For any n, An is countable. Hence fourth one is definitely correct. Now say I am defining A1 to be 0, A2 to be minus 1 comma 1, A3 to be minus 2 comma 2. In this way, An plus 1 to be minus n comma n. Then An intersection Am is clearly empty by our definition. Union of An greater or equal to 1 is Z, and so An is finite for all n here, right? Hence second one is third option is also false. N is infinite for some integer, that is also false. Okay, now only two options left. An is finite for every integer and An is finite for some integer. Okay, so for counter example for 1, that is also easy to construct. Counter example for 1, say A1 equal to negative integers union 0 1 and an equal to singleton n for n greater or equal to 2, then clearly union of an equal to z, and any to have non-empty intersection, sorry, empty intersection, but a1 is infinite, right? Hence this one is also false. Now second one is slightly tricky, but we can do it. How do I define it? So I will define it starting from a2 and I will define a1 later. So how do I define it? So see, n is countable, right? This will imply n minus singleton 1 is countable, and p equal to defined as set of all primes. So this is also countable. That means we have a bijection psi is a bijection. We can always have a bijection, right? Now I define an equal to x belongs to natural number such that x equal to fn power k for some k greater or equal to 1. Okay, so let, without loss of generality, assume that say n equal to 2, f of 2 equal to 2. I defined, say, that means a2 is given by 2, 4, 8, 16, 32, 40, 64 and so on. Okay, say for n equal to 3, I am defining f3 equal to 3, then a3 equal to 3, 9, 27, 81 and so on. Similarly so on. For n equal to say 4, I am defining f of 4 equal to 5, because I need to define a prime number, right? So a4 is given by 5, 5 square, 5 cube and so on. And a1 equal to x belongs to z such that x not contained in an for all n greater or equal to 2. That means I am taking the complement of all this number. Okay, so that means clearly with a1 intersection an is empty by definition, right? a1 intersection an is empty, and also union of an equal to z, because after taking union n greater or equal to 2, I am defining a1 to be complement of that inside z. That means whole union gives me the entire set of integers. So I need to only check that an intersection am is empty for any nm greater or equal to 2. An intersection am is empty for any n greater or equal to 2, nm greater or equal to 2. That is quite obvious, because the set an is basically the prime powers, right? Now if 3 to the power k1 equal to 5 to the power k2, that cannot happen for any k1 or k2 greater or equal to 1, right? So that is simple. Hence an intersection am is empty. Fine. Now you can observe that all ans are infinite here, right? All ans are infinite here. Hence the second option, which is saying that an is finite for some integer, that is also false, because here for all n is infinite. Very good. Now move to next one. So p from R2 to R be a function defined by projection on first coordinate. So p of x comma y equal to x. So that is projection on first coordinate, right? Then which of the following is true? Let's draw the picture. So x square plus y square less than 1. So if it is say minus 1, if it is 1, then we have this, because it is less than 1. That means this boundary is excluded. So it is basically unit disk. And boundary is excluded from the set. Now if you project it, projection on x-axis, you will get -1 1 open interval, right? Right, -1 1 -1 comma 1 open interval, and that is an open set. Hence this is true, because this is the definition of. So see, here everything the saying that for each y belongs to this image, there exists a positive real number epsilon such that this holds. That will imply that P of A1 is open set. For each condition, it is saying that P of A1 is open, P of A2 is open, P of A3 is open, P of A4 is open or not. That, right? That is the question. So clearly -1 comma 1 is an open set. So P of A1 is open. This one is correct. Sorry, this one is correct. Now move to second one. Second one says saying that the unit disk with boundary. So then for A2 this will be -1 comma 1. Hence clearly this is not open. If you take 1 or -1, then you can't have any epsilon such that this is contained in that. So this is not an open set. So second one is false. Third one is xy equal to 0. So xy equal to 0 means, so xy equal to 0 means it is basically two axes. It is basically two axes, right? So that means if you project it, this will becomes the x-axis. Hence it is open set. So this is also correct. Sorry, this one. And A4 equal to xy equal to 1, right? A4 equal to xy equal to 1. So that means it looks like, if I draw the picture, is something like this, right? So if I project it, we will have r minus 0, which is also an open set. 0 is not there, but it is r minus 0, which is also an open set. Hence this is also true. Hence except second one, 1, 2 and 4 are correct answer. Okay, so basically the given point is for any lambda there exists an epsilon such that y lambda minus epsilon comma lambda plus epsilon is contained in the image. That basically saying that the image for every given set A1, A2, A3, A4, whether the image is open or not. That is important. And here this the map is that projection on first coordinate. So just draw the set and take its projection on first coordinate and see. It's a very simple problem if you understand the definition very properly. Now move to the next one. For real numbers a, b, c, d, e, f, consider the function f from R2 to R2 given by this. Which one of the following are true? See, f is continuous. That is very simple, because f is R2 to R2, so component function, we can check the component function. So first component is ax plus by plus c, which is basically a kind of linear map, and that is kind of linear map, not linear, but it is easy to check that this is continuous by definition, right? Now f is differentiable. That is also true, because in particular you can take its Jacobian matrix. The Jacobian matrix is given by A, D, B, E, right? So f is differentiable. Also f has partial derivative of all orders, right? So by definition it is true. Now some students have doubt that f is uniformly continuous or not. So you don't need to think it very much, just go by the definition. So f is uniformly continuous. If I need to show, what do I need to show? I need to show that since it is in R2, so I can take this f of x1 comma y1 minus f of x2 comma y2. So I need to show that for epsilon greater than 0 given, there exists delta such that less than delta implies this holds, right, by definition. So see, f of x1 comma y1 minus f of x2 comma y2 mod, or you can say its norm, it is basically given by a x1 plus b y1 x1 plus b y1 plus c comma dx1 plus dy1 plus f e comma minus ax2 plus by2 plus c, so and comma dx2 plus ey2 plus f, right? So what is this by definition? It is basically root over a this x1 minus x2 plus b y1 minus y2 this square plus root over plus root is there d x1 minus x2 plus e y1 minus y2 d x1 minus x2 plus dy minus y2 whole square, right? Okay, so that means it is root over a times x1 minus x2 plus b times y1 minus y2 plus this. Now take maximum of abcd, maximum of abcd, say this is k, that means this is less than equal to k times root over x1 minus x2 square, k 2 times x1 minus x2 square plus 2 times y1 minus y2 square, which is same as k root 2 times root over x1 minus x2 square plus y1 minus y2 square, and that is same as k root 2 times x1 comma y1 minus x2 comma y2, this, right? So hence this function is basically a Lipschitz function. Okay, hence this is uniformly continuous. Okay, so since it is Lipschitz, so this is uniformly continuous. Okay, hence this all the options are correct. Move to the next one. So f from R to R be a continuous function such that mod fx minus fy is greater or equal to log of 1 plus x minus y. This question came in TIFR exam, TIFR PYQ. This is the same problem is in TIFR PYQ. Okay, so see, so if fx equal to fy, that will imply mod fx minus fy is 0. That will imply log 1 plus mod x minus y, this is 0. That will imply x minus y is 0 equal to x equal to y. So f is 1 1, right? And f is given to be continuous, right? Now how do I show that whether f is onto or not? So f is continuous and f is 1 1. That means f is strictly monotone. So either it is monotonically increasing or it is monotonically decreasing. First observation. So observation number 1, f is strictly monotone, strictly monotone. Okay, and secondly, whether f is onto or not, if I want to check, it is enough to check that when x goes to infinity, f goes to positive infinity or negative infinity, or what do I want to mean? Let's write. So if x goes to infinity, say fx goes to infinity or minus infinity, and if x goes to negative infinity, fx goes to negative infinity or infinity. If I can show this, then we are done. Why? Because f is continuous. So if I can show that f attains a and b, that will imply f attains all the points in between a and b by intermediate value property of a continuous function. So it is enough to check whether f tends to positive infinity and negative infinity as well as, right? So, and since f is monotone, so if f goes as x tends to infinity, if fx goes to positive infinity, then when x goes to negative infinity, fx must goes to negative infinity because it is monotone, right? And that we need to show. Okay, if we can show that, then f is onto. Now how do I show that? Say fx minus f0 is greater or equal to log 1 minus mod x. Let x goes to infinity. That will imply mod fx minus f0, that goes to infinity. Now f0 is a finite quantity, right? So that will imply fx goes to negative infinity or fx goes to positive infinity, right? It can't be oscillatory. That is important here, right? So from this line I can conclude this line because f is strictly monotone. F is strictly monotone. So it may happen that fx goes to negative infinity, so that mod fx minus f0 goes to infinity because we are taking mod, or fx goes to positive infinity. So fx minus f0 mod tends to infinity. Okay. So here it is very important that f is strictly monotone. That's why this happens. Now without loss of generality, you can assume that as x goes to infinity, fx goes to positive infinity. And since f is strictly monotone, then when x goes to negative infinity from that same condition, because it is mod condition is there, so I can take x goes to negative infinity, we will have fx goes to negative infinity. Fx cannot go to positive infinity in this case because f is strictly monotone. So we already know that for a large enough x, the value of fx is large enough. So as well as in large enough negative x, value of fx must be large enough negative. Otherwise, this cannot be strictly monotone. So in this case, we are assuming that f is strict. So when x goes to infinity, fx also goes to infinity. That will imply f is strictly increasing. So that means x goes to negative infinity implies fx must goes to negative infinity. Or if x is strictly decreasing, then when x goes to infinity, fx goes to minus infinity, and when x goes to negative infinity, fx goes to positive infinity. In case of f is strictly decreasing. So hence, since f goes to negative infinity as well as f goes to positive infinity, that means it must attain all the values in between this. So hence f is onto. Okay, hence f is onto. So here it is very important that f is strictly monotone, and that is very important result from real analysis, that continuous 1 function is strictly monotone, and you can prove it. The proof is also simple. Okay, and you can find it from any book. Okay, now move to the next one. Okay, so the function a from R to R is defined by fx equal to box x sine 1 by x and 0 for x equal to 0. Okay, has a discontinuity which is removable. So what is the meaning of removable discontinuity? That means limit x tends to a plus fx equal to limit x tends to a minus fx, but f of a is not equal to this limit, then we can remove that limit and define it so that f becomes continuous. That is the idea, right? Removable discontinuity. Removable discontinuity means, say you have this and this, but somehow at this point a, f is defined in this way, so you can remove this and give this value this so that f becomes continuous. Okay, fine. So at first, to have removable discontinuity, we must, this limit must be exist and be equal, right? So as x is greater than 0, so close to 0, and x is greater than 0, that means box is equal to 0. So fx equal to 0 when x is near 0 but x is positive. But when x is negative, then box x is minus 1, right? So when x less than 0, so box x is -1. So box x is -1, and that means fx equal to minus sine 1 by x when x less than 0 and close to 0. But that limit doesn't exist because sine 1 by x at x tends to 0 limit doesn't exist. Hence left hand limit doesn't exist. So this removable discontinuity, this is wrong. Move to the second one. Fx equal to sine log x for x not equal to 0 and 0 for x equal to 0. You can check that this is not removable. That is true because limit here f is defined on closed interval 0 comma infinity. So it is enough to check the right hand limit. So limit x tends to 0 plus sine log x, that doesn't exist because sine is continuous function. So I can write it sine limit x tends to 0 plus log x, but that doesn't exist, right? Because limit x goes to 0 plus log x limit doesn't exist. So that will imply that this is removable this is not a removable discontinuity. Hence this option is correct. Now move to the third one. Okay, so see fx equal to e power 1 by x when x less than 0. So if limit x tends to 0 minus f of x equal to limit x tends to 0 minus e power 1 by x. Okay, so say xn equal to say minus 1 by n. Okay, say xn equal to minus 1 by n. Then xn goes to 0. E power 1 by xn equal to e power 1 by minus 1 by n, which is 1 by e power n. That goes to 0. So that goes to 0 as n goes to infinity. So since x is negative and x goes to 0, that means e power 1 by x exists and the value is 0, right? So limit x goes to 0 minus f of x, I am giving it as an example that if you particularly take xn to be minus 1 by n, you can easily see that this is goes to 0. And this limit exists, which is simple to check. So limit x goes to 0 minus fx is 0. Now what about f of 0? F of 0 is e power 1 by 1 plus 0, which is e. And limit x goes to 0 plus e power 1 by x plus 1 is e. So that means it has jump discontinuity because left hand limit, say this is left hand limit is 0, right hand limit is e, so there is a jump, right? There is a jump, so it is jump discontinuous at 0. It has jump discontinuity. So third one is also correct. Now fourth one is f and g from 0 1 to r be two function of bounded variation, then their product has at most countably many discontinuities. So first of all, there is a very important result, theorem of Jordan. A function is a bounded variation if and only if it can be written as difference of two monotone function. Right? And we know that any monotone function has at most countable many discontinuity, and it is written as difference of two monotone function. That means any bounded variation, if a function is bounded variation, then it has at most countable many discontinuities, right? So f and g both have countable many discontinuities. That means fg has at most countable many discontinuity. So fourth one is also correct. Okay, hence 2, 3, 4, these are correct answer. Okay, move to the next one. It's a very nice problem that for a differentiable surjective function f from 0 1 to 0 1, consider the function capital F is given by f of x comma y is small fx comma small fy, and f prime x is not equal to 0 for every x. Okay, then what we can say? Okay, so let f of x comma y equal to f of u comma v. So this will imply fx comma fy is f of u comma f of v. This will imply fx equal to f of u and f of b equal to f of v. Now f prime x is not equal to 0. This will imply f prime x strictly greater than 0 or f prime x strictly less than 0 for all x. Because if for some x1 f prime x1 greater than 0 and f prime x2 is less than 0, then since derivative of any function, differentiable function satisfying IVP, so there exists some point such that f prime x is 0, which is a contradiction. That means either f prime x is strictly positive for all x or f prime x is strictly negative for all x. Not from in R, it is from open interval 0 1. Hence either f is strictly increasing or f is strictly decreasing. So f is monotone. So that means capital F is injective, because f is strictly monotone, so f is injective, so capital F is injective. But second one is false, because here it may happen that f prime x is strictly less than 0. We have given condition that f prime x is not equal to 0, so it can happen that f prime x is strictly less than 0. In particular, since the map is from 0 1 to 0 1, you can take fx equal to 1 minus x, right? So f prime x is minus 1, which is less than 0, and f is decreasing. Hence second one is false. This for every x prime comma y prime, there exists a unique such that this holds. Okay, so let x prime comma y prime belongs to 0 1 cross 0 1. F is surjective and f is injective by given condition, right? That means f is bijective on 0 1. So that means there exists unique u belongs to 0 1 and v belongs to 0 1 such that f of u equal to x prime, f of v equal to y prime. So in particular, f of u comma v equal to x prime comma y prime. And since this is unique, hence for capital F, this is unique. This is correct. And total derivative dfxy is given by the Jacobian matrix is del f del x, del f del y, sorry, del f1 del x. So if f is given as f1 comma f2, this is del f1 del y, this is del f2 del x, this is del f2 del y. So this will imply f prime x 0 0 f prime y. So the determinant dfxy is given by f prime x times f prime y, which is not equal to 0. Hence this matrix is invertible. Total derivative dfxy is invertible because f prime x is non-zero for all x. Hence f prime x times f prime y is also non-zero for any xy belongs to open interval 0 comma 1. So this one is also correct. So this is correct. So 1 3 4, these are correct answer. Now move to the second one. Sorry, the next question. So for any real number lambda, consider the improper integral. Okay, so let's I lambda is given by 0 to 1 dx by 1 minus x to the power lambda. So if 1 minus x to the power x equal to z, then minus dx equal to dz, right? So that means it is 1 to 0 minus dz by z to the power lambda. which is same as 0 to 1 dz by z to the power lambda. 0 to 1 dz by z to the power lambda, and k lambda is given by 1 to infinity dx by x to the power lambda. Okay. So that means this is there, right? Okay. Now we know that this is the theorem from improper integral. From improper integral, this is result. You need to read this theorem, improper integral, that k lambda exists if lambda greater than 1. I mean k lambda is convergent. Better to write convergent if lambda greater than 1, and divergent for lambda less equal to 1. And I lambda is convergent, the reverse, for lambda less equal to 1, less than 1, and divergent for lambda greater equal to 1. Okay. Now there exists a lambda such that I lambda converges but k lambda doesn't converges. So take say lambda to be 0. Okay, take say lambda to be 0, then clearly k0 doesn't exist but I0 exists. Right? You can in particular compute that integral, because if you took here lambda to be 0, then this is 0 to 1 dz, which is z. So I0 equal to 1, but here I0 doesn't exist. Okay. Similarly, there exists a lambda such that k lambda converges but I lambda doesn't come. In particular, you can take lambda to be 2. Right? So these two are correct, and fourth one is also correct, in particular if you take lambda to be 1. Okay. So hence 1, 2, 4, these are correct answer. Move to the next problem. So suppose f from -1, 1 closed interval to r is continuous. Which of the following implies f is identically 0 on -1, 1? So observe that the domain is given by -1, 1. So suppose you have a odd function such that that means gx equal to g of minus x. Okay, for all x belongs to say 0, 1, then -1 to 1 gx dx is 0, right? Sorry, if it is odd, right? So we are trying to use that. So let's say for third one, it is given that integral -1 to 1 fx times x to the power n dx is 0 for n greater or equal to 0 odd, right? So take fx to be constant function, any constant c. Okay, then -1 to 1 c times x to the power n dx, and x to the power n, since n is odd, this is an odd function, so that means this integral is 0. But you can take fx to be c, where c is any non-zero constant, so f is not identically 0, so this one is false. Okay, now fx equal to -1 to 1 -1 to 1 fx x power n, but n is even. So in particular you can take fx to be any cx, right? Then c into -1 to the power 1 x to the power n plus 1 dx, and since n is even, n plus 1 is odd, so by similar condition this is also 0, but f is not identically 0, right? So c and third one and fourth one is false. Now first one says that -1 to 1 fx times x to the power n dx is 0 for n greater or equal to 0. So first one and second one, so first one implies second one, and second one also implies first one. So 1 and 2 are equivalent. So if one is true, because you can write this one, right? -1 to 1 fx times px dx equal to, you can write -1 to 1 fx times say a0 plus a1x plus akx to the k dx. So you can write it as a0 minus 1 to 1 fx dx plus a1 minus 1 to 1 fx times x dx and so on, ak minus 1 to 1 fx times x to the power k dx. So if all the terms are 0, so that means this is also 0. So both are equivalent. And in particular, if conversely you can take px to be any polynomial like x power n. So these are equivalent. So 1 and 2, either 1 and 2 both are correct or 1 and 2 both are false. So to solve that, I have already made a video regarding this type of problem. If anyone see it before, then definitely they can answer this question. So the theorem, very important theorem, that is Wester's approximation theorem. What the theorem says that for any epsilon greater than 0 and any f continuous function on some closed boundary interval ab, there exists a polynomial px polynomial such that mod px minus fx is less than epsilon for all x belongs to a. And then I have already made a different video for this, but now it is your homework to show that minus 1 to 1 mod fx square is 0 from minus 1 to 1 fx times px equal to 0. You have given this, then from that you need to show that minus 1 to 1 fx whole square is 0. Now fx whole square is always positive, and on an interval it is 0. That will imply fx is identically 0. Okay, that will imply fx is identically 0, because f of x whole square is identically 0, so fx is identically 0. Hence 1 and 2 are correct. Okay, move to the next one, and I hope there are only two questions left. So fn be a sequence of functions defined on closed interval 0 1 by fnx is x power n log 1 plus root x by 2, right? Okay, so x 0 less equal to x less equal to 1, so 0 less equal to root x less equal to 1, so that means 1 by 2 less equal to root x, sorry, 1 plus root x by 2 less equal to 1. So that means log of 1 by 2 less equal to log of 1 plus root x by 2 less equal to 0. Okay, this is the case. Okay, this is given. So that means in particular this log part is bounded, right? Okay, so first say x equal to 0, then clearly fnx is 0, and for x equal to 1, log of 1 plus root x by 2, which is log 1, which is 0. So for x equal to 1 also fnx is 0. So that means for x equal to 0, fnx pointwise converges to 0, and for x equal to 1, fnx converges to 0 also. Now for 0 less than x less than 1, this part is bounded, right? And x to the power n goes to 0 as n tends to infinity, because x is in between open interval 0 and 1. So in particular fnx goes to 0 as n goes to infinity. So hence fnx converges to fx pointwise on closed interval 0 1, where fx is identically 0 function. Now whether f is uniformly convergent or not, to show that I can define a sequence mn belongs to 0 1 such that mod fnx minus fx. Now fx is identically 0, so that will imply supremum x belongs to 0 1 mod fnx, right? It is same as supremum of x belongs to 0 1 times x power n log 1 plus root x by 2. So, and we are taking mod, right? So this is less equal to supremum of x belongs to 0 1 mod x to the power n times log mod log half, right? So hence from there supremum is 1, so we can get less equal to mod log half, this condition, right? So we can't conclude from this mn, right? Then how do we do this? So for this particular question you need to use some very strong result which is called Dennis theorem, that you can find in any book where you have read this theory of sequence and series of function. So what is Dennis theorem saying? That Dennis theorem says that if you have fn is a continuous function on compact sets and fn is monotone, continuous compact set, fn is monotone and fn converges to f pointwise and f is continuous, then fn is uniformly convergent to f uniformly. Now here fn is continuous for each n. Here the set is compact because closed interval 0, 1, right? Here also fn is monotone. Why fn is monotone? Because see, x to the power n plus 1 is less equal to x to the power n, and x to the power n times log of 1 plus root x by 2 is greater equal to x to the power n times log of 1 plus x root x by 2. Why this is reverse? Because log is negative in this region, so this is greater equal, but ultimately it is monotone, right? So f of n plus 1 x is greater equal to f of fn x, so it is monotone increasing, and the limit function f is identically 0, so that is also continuous, right? Hence by Dennis theorem it is uniformly convergent. So in particular for this case we can't use, most of the cases we are trying to use this mn and trying to find whether mn goes to 0 or not, but here we can't conclude, right? So that's why we need to use some advanced theorem, and the advanced some strong result, and that is Dennis theorem. So by using Dennis theorem, fn uniformly converging to 0, 1, and also fn uniformly converges to, sorry, pointwise converges to 0. So these two are correct answer. Now move to last problem. So the last problem says that x be any real number and which one of the following statements are true. First you need to understand that what is the meaning of this theorem, what is the meaning of this statement. So x belongs to real number is given, so there exists a integer n greater or equal to 1, that means there exists a natural number in particular such that if I write this sequence as n, so there exists k belongs to n such that ak is greater or equal to x. In particular it is equivalent to saying an is unbounded, right? It is equivalent to saying an is unbounded because you are choosing any x. First you can take x to be any large enough real number, and if there exists some k such that ak is greater than that large enough real number, that will imply that an is unbounded, right? N is unbounded. So we need to check that whether an is unbounded or not for every sequence. Okay, fine. So first sequence is an equal to n square sine 1 by n. So you can write it n times sine 1 by n by 1 by n. Now see, sine 1 by n by 1 by n goes to 1 as n goes to infinity. Why? Because we know that sine x by x goes to 1 as x goes to 0. So as x goes to 0, sine x by x goes to 1. So hence in particular 1 by n also goes to 0. So sine 1 by n by 1 by n, that is goes to 1. But there is a term n outside, hence an is unbounded. So this one is correct. Okay. Now n times cos 1 by n. So as n goes to infinity, cos 1 by n goes to cos 0, which is 1, and there is a term of n, right? There is a product term with n. That means n cos 1 by n also unbounded. So second one is also correct. But third one is wrong. Why? Because as n goes to infinity, n by e power n, exponential function is increasing more faster than linear function, right? So e power n is diverges to infinity more faster than n. So n by e power n, in particular you can find the limit. So n by e power n goes to 0 as n goes to infinity. Hence n by e power n is not unbounded. So this is false. And the fourth one is n by log n, right? So n by log n. So as n goes to infinity, so it is n by log n, right? So as this is infinity by infinity, in particular you can take a function fx to be x by log x, and that is infinity by infinity function. So by using L'Hopital, you can just take limit x tends to infinity, x by log x is basically given by tends to infinity 1 by 1 minus x, which is infinity, right? That means it is also unbounded. So fourth one is also correct. Okay, so hence 1, 2 and 4 are correct answer. Third one is wrong. Okay, so I hope all the solutions are clear to all of you. If you have any doubt, just comment below. Thank you.